Hello, everyone. Nobody's here, so I'm just gonna get started and hopefully I'll get to watch the recording later. So yeah, this is going to be the XFLR workshop, and the first thing I need to do is cover the basics. So let me share my screen. Hopefully you'll see what I'm seeing, right? And y'all do. Y'all should. So yeah, XFLR workshop by me. With XFLR, it's an open source software tool for the design and analysis of airfoils, wings, and planes. Basically, it helps you make planes. But let's see, I'll guide y'all through how to download it if y'all have any trouble with that. XFLR5. Either one of these links work. This one, the source code one just directly takes you to the download. Um, you just click download and you should get the most latest version of it, which is, to my knowledge, 6.61. Now that that is covered, let's go to the next area. So airfoil databases. So the most fundamental part of aerodynamics, our team is designing the wing and the empennage. The shape these parts of the plane take is defined by an airfoil. So there's two ways to get airfoil data. One is through NACA files and one is through DAT files through the UIUC database. I'll show y'all how to import and make it all work in XFLR and soon. But first, let's see these databases actually look like. So for specifically NACA files, there's this thing called the airfoil tools or something. Wait, NACA airfoil tools. Yeah, should work. Sometimes it crashes. So you can click through all these airfoils for NACA, 4 digit, 5 digit, and 6 digit. Usually do 4 digit or 5 digit, most of the times 4 digit. So these are just examples of some of them. Some of these like flatter ones with no camber, they are usually used for the empennage. This could be used for a wing. This is definitely for a wing. So and the other way to get airfoils is through the UIUC database. These are, I think you can probably find NACA files on here. Generally, they're airfoils that aren't classified under NACA, and there's like a whole history behind why there's a distinction. But um, to we don't really need to get too deep into that. Y'all can research into that if y'all want. Um, but yeah, these are NACA non-NACA airfoils. And also, okay, yeah. So now I'm open XFL. Hopefully it works. So yeah, just to streamline stuff, I'm going to use a file that's already been made, but I'll show y'all how to edit and all that stuff so that y'all get to, you know, all along it. So I'm currently in plain wing and plane design. That's what, yeah, wing and plane design. When you get started, the first thing you do when you're on that blank screen is click module and click soil direct analysis. I already have a bunch of airfoils in here, mostly with the help of the project leads. Thank you, by the way. I was about to go. So, anyways, um, the first thing is NACA foils. So No, you can enter a 4 to 5 digit number for it. There is a distinction between the two, but it's not super duper important exactly. So um, get into that later. It's not like the most urgent of things. So we could say NACA 000009, and I'll just enter 009. Number of panels, it'll say 100. Usually it'll do like less than that. It really just depends on the shape of the airfoil. So, it gives you this, you just click OK, and you should have this airfoil with you right now. And I will also, this is one commonly used for an empennage, so I will also um, use one that is commonly used for a wing, and we could just use the first one we see, which is 2414. Yes, 2014. Okay. And we now have two distinct airfoils. This one and this one. These two. NACA 0009 and NACA 2414. And the next thing would be to import a non-net. So what I do then is I just, depending on the criteria, what type of airfoil we use changes. Some years we need more stability, some years we need more lift, and it really just depends on the competition. So just pick a random one for now. If you just directly click it, it'll take you to the coordinate points you need to graph the actual airfoil. But oh wait, I hit the page. So yeah, the previous window tab you saw was the coordinates of these unique airfoils. I think I did E something. E doesn't really matter. E16. So you don't want to directly click it. You can directly click it if you want to look at those coordinates. What you'd want to do is right click it and click save link as, and it will save as a def file by default. And let me see if I do not have this one. Save and yes, and always before you do anything new in the in XFLR, always click the save button, right? So we currently have two airfoils. I am about to add a third. To import a non-NACA airfoil, you click File, you click Open, and then you find that airfoil. I think it was in my desktop. We did E16. Oh, yes. E216 is right about here. I'll click Save after because that was something new I did. Now you can see this general shape of this airfoil. And the next thing we need to do is called batch analysis. What is a batch analysis? It basically runs through a different angles of attack at increments and at different Reynolds numbers, and it gives you data like, wait, let me clear it. Actually, it gives you data like the coefficient of lift, different angles of attack, the coefficient of drag, the CL to CD, the coefficient of lift to the coefficient of drag, which is basically a description of stability. Right? Let's see. You need these exact Reynolds numbers, or none of the other analyses will work, right? So it goes from, if you look at this, look at these numbers, right? It starts at 1,000, it goes up to 5 million. 1,000 being like barely anything. See, the thing with Reynolds numbers is that it's a dimensionless number that describes the laminar or turbulent flow. The higher it is, the more turbulent the flow is. Right? So in here, we have 44 Reynolds numbers, as I said, going from 1,000 all the way to 5 million, right? 1,000 is like being on the moon, and then 5 million is like being on Jupiter. Actually, what we're concerned with is like the about from like about 80,000 to like 400,000, which should be enough for us. I'll click E216. You can select different airfoils that you want to analyze. I will click ET16, E2412, and NACA 0. And the ones highlighted in blue are the only ones it will analyze. Right? You know, I can increase, decrease the element. We are doing a lot of angles of attack. We're going from -20 to 45. So it might take a while. Hopefully it doesn't. But yeah, if I decrease this increment, it'll just take longer. Another important thing is the threads, right? These threads. Threads basically describes how much power your power or CPU power, I guess you could say, your um, laptop will use will dedicate to do these analyses, right? The more threads you use, the faster it can be. And you have more threads if your computer is more powerful. Mine can do up to 14. Yours might be like 32 or something, right? It really depends on the laptop you have. Right? We'll get into like the mock and critical and all of that later. So one more important thing, when you add or delete a Reynolds number in this box. So when you see this action tab, right? Click the three dots. You can say insert password, and it'll automatically give you a Reynolds number, but you can change it. You can change. See, it gave us like 1,500, but maybe I want it to be like 1,900, and all I do is that, right? Yeah, it's as simple as that. And if you don't want it, you just click delete. And if you want one like that's before Reynolds number that you're on, the Reynolds numbers that's highlighted, you just say insert before, and it'll give you something lower. Maybe I don't want 500, I want 900. And for this case, I really don't want to do that, so I just click delete. Simple as that. So yeah, you want the polar types. We're still looking into what these polars actually mean. More information will be provided on that in the future. Force transitions, we're also looking into that. It has to do with what part of the airfoil experiences more force, to my understanding. But yeah, we'll definitely look into that because that could be very helpful in the future. And you could say start from 0, but in our case, we don't want to do that. We want to start from -20. So I'm gonna double check if all the airfoils I want to analyze are selected. E216, NACA 0009, and NACA 2414. Okay, I'm going to click analyze. I do have a lot of things open at once. It's just taking its sweet time. And also one thing, do not get scared of all these lines. Right? I mean, each one's just an individual airfoil. Like, I know it might look scary, but the more you look at it, the more you get used to it, and you know, it's it's not that deep, really. So now we're just waiting for this analysis to complete. By the way, I'll try to keep this under an hour 30 because I've got stuff to do. And watching that long video might be kind of. Also, I didn't start recording till around 20 minutes. I don't know if those first 20 minutes will be in the recording. The first 20 minutes of this meeting was literally just me waiting for people to join. And no one joined. So, here we are. As you can see, it's currently on 0009. I hope I can scroll up, and now it's on starting E216. And are more advanced and demanding analyses that we'll need to do. If they don't work, um, if XFLR crashes, then I'll probably have to do it in person with people. We'll see. It's it's complete. It didn't take as long as I thought it would. So let's close. So we have all these Reynolds numbers, and I am going to ensure none of the airfoils I don't want to look at are visible so that I don't get overwhelmed by this. Before that, I'll click save. It's going to tweak if I don't do that. Take a while, guys. Okay. This. Oh, okay. This side. Don't worry about that, guys. This over here doesn't. Okay. Yeah. Um, It's just a thing to see analysis settings. So this is more important for the other analyses we're going to do. So don't worry about it for now. So I'll want to look at 2414, right? So as you'll saw, as I click the X's, the corresponding lines, or polars as they're called, each of the following airfoils disappeared. But what if I want them to not disappear? I want to see them, right? Just click, um, you just click it, it should be visible. I also want to look at NACA 0009, so I'm not going to put the X on that, but all these other ones can go. And there should be an easier way to do that. Say tidal polars. Yeah, that made it everything. The three that I want to look at are NACA 00, 2414, 216. So first we'll look at 2414. Hopefully it works. Um, Typically, say deciding an airfoil or a wing, okay, this is what you'd want to see. Sort of this, like, I think, mm, a logarithm. Like, don't worry about all of this. That's because he started from a negative point, so then it like curves back, sort of. Graph is supposed to do that. Um, Start about it from like 0 to like what you want to see. So this is the CL to CD graph. As Reynolds numbers are increasing, which is like going this way. So the very top, tippy top line you see is the lowest Reynolds number. As you go, Reynolds numbers increases. That's why it gets crazier, right? Because obviously the plane will be less stable when it's experiencing more turbulence. So let's see out. Low Reynolds numbers, the coefficient of lift will slowly increase, and then as it decreases, coefficient of drag increases, which is the x, right? Typically, you want coefficient of lift to be like, and from like 0 to like around the highest I've seen is like 3, and then coefficient of drag should stay under 1, like really under 1 for an airfoil, especially one that you want to use for a wing, right? So as you can see, the graph doesn't go beyond 0.15. Next thing we have is coefficient of lift um, to alpha or angle of attack. So this is like, you want to see this as at least a general increase, right? When you're looking at airfoils or wing. However, this one is, I guess, for if you're just building a plane, right, it'll be fine. It's saying that at 0 angle of attack, the airfoil will have no coefficient of lift, which basically means no lift. In some cases, that's bad. In some cases, it's not. It really depends on what you want out of your plane. Right? And then the pitching moment, that's like the stability of, is it gonna pitch down, pitch up? And this is like, it should stay around 0 ideally. This one might not be that stable, at least pitch wise, because it's like sort of all over the place, and it's more towards the pitch down than it is the pitch up. And then coefficient of lift to exterior top. Basically, think of the top part of the airfoil. We can go back to the full direct analysis. Hopefully, oh, yes. So you want to look at the airfoil again, you just click this button. Look at the graphs, you click this button. That's airfoil. So going back to what I was trying to explain, coefficient of lift, exterior top. What that means is that this top part of the airfoil, each part, each individual section, will experience a different amount of, let's say, of the Reynolds number. Let's say like the lift, right? Each part of the um airfoil, the top part will experience a different amount of force. Is lift, it's not exactly a normal, like a traditional force, it's more like pressure. So different parts of a body can experience pressure a little bit different. There might be more pressure at the tip, at the leading edge, than there is at the trailing edge, right? What this graph does is explain that, right? So let's see here at like 0 exterior top, which is like the leading edge, right? There is a lot of lift. Coefficient of lift is like exponential. But that, like say 1, right, which is like we could assume that's the trailing edge, there's not that much. It decreases. The amount of lift each part of the airfoil, the back section of the airfoil experiences is not as much front section. Does that make sense? So we're done with like the mathematical part really. I could go on to explain the other schools we chose as well, but time constraints. So we'll move on to different of this. So plane design. Some important things to keep in mind is the chord, which is like the width of the wing. When you're thinking about it as a 3D shape, the chord is sort of like the width of the wing. But when you're just thinking about an airfoil, it's the length of the airfoil. So we have this airfoil, right? It's from what is the length from this leading edge to this trailing edge. This is what chord is. Wingspan, that's just the um length of the plane. No, my bad. Length of the wing. That's what I meant. Length of the wing. Wingspan's in the name. Length of the wing. Horizontal stabilizer typically really depends on again what you want out of this plane, right? So it's going to be like 30 to 60% of the wingspan, and then vertical stabilizer is going to be 30 to 40% of the horizontal stabilizer. So say, let's do some quick math here. So say you have a 1 foot plane, right? Horizontal stabilizer would ideally be like around maybe 40% of that 1 foot. How many inches are in a foot? 12. So 40% of the 12, which is like, I have to use a calculator for this. 4.8. Yeah. Well, open chat GPT instead. Did GPT did it this time. GPT. Say 12 inches is our wingspan, right? What would our horizontal stabilizer be? We could choose anywhere between 30 to 60%. 60 is like really pushing it, honestly. So I'll say 40%, right? 0.4, 4.8, around 9. I mean, I'm around 5 inches, right? And then the vertical stabilizer is 30 to 40% of the horizontal stabilizer. If our horizontal stabilizer is 4.8 inches, it's going to be, let's try 20% of that. So we expect it to be 2 inches. Well, I'd say honestly, like, hmm, let's change this to wingspan, guys. My bad. I'm still learning. You know, I've been doing this for 2 years and I'm still learning stuff. So sometimes I do make mistakes. 30 to 40% of the wingspan, right? So we did 40% for the horizontal stabilizer and we got 4.8. So we're going to try, I'd say 30%. So yeah, that sort of makes more sense. Right? So let's see here. We got example, right? 12-inch wingspan, and then your horizontal stabilizer, horizontal babe, 12 inches give or take. And then vertical would be give or take. And that could work. That should work, honestly. And then, yeah, now to make this reality in XFLR. So what will I do first is I will go to model and plane design. So once you want to start designing your wing and your empennage, you go to wing and plane. You already have some models here. We're going to make a new one for this workshop. Plane, you go to plane, you go to define a new plane, and then, yeah, let's name this underscore. And define, um, this is, first before anything, I'm going to check my units as I sort of eyeballed the, the dimensions I wanted in inches, so I need to make it so that, okay, so to any time you want to check units, any settings, you go to options, preferences, and you can have updates, save options. Um, okay, so it auto saves every 17 minutes. That's not, yeah. No. Okay, yeah. So you can set it to autosave. I don't know if it works. I'll say like every 2 minutes, honestly. And then language, they have 5 languages, so many. And units, this is what we care about. So units, so this to inches, right? Closed. And then workshop plane. I right click that. And then, so first we need to assign a main. Um, let's see here. We decided 12 inches, right? So when you enter the span, right? So y parentheses, it's along the y-axis. You want to enter half of it. Because it's counting from like the origin in one direction, right? But then it overlaps it in another. So I'm going to say 6, right? And then we have a pretty small plane. We're making a pretty small plane. Chord, uh, we said length of the, you know, honestly, we don't want this to be too goofy looking, too big. So say uh, 4, 5 inches, I guess. And for now, we're just gonna work with like a normal, nothing fancy wings. So just offset to 0. Make sure this is all 0. Make sure twist is 0. Twist is like it literally twist the the wing. So, we have all these airfoils set up. So if you want to set a foil to your wing or your empennage, you have to do a batch analysis on it beforehand. So let's see here. NACA 2014. And then you also have to define the bottom. You can define a top part of the airfoil and a bottom part of the airfoil. We're looking into that. That's probably going to be something we really dive into like next year or next semester. So, so yes, now you have a wing, as you can see. So we don't really need to concern ourselves with this part. It's just like the paneling and stuff. It really doesn't matter now. Maybe towards like the end of the year when we're writing like the final report and we need like really accurate results, maybe we'll look into this part. But for now, don't concern yourself. It's fine. Click save, and then we'll move on to the elevator and the fin. So, okay, so XFLR calls the horizontal stabilizer, the entire horizontal stabilizer, the elevator. Technically, it's like the same thing, but elevator for us is like more specifically the control surface. Like the horizontal stabilizer is like one chunk of the empire, right? So we'll get into control surfaces and all that later. I'll actually try to have another workshop, right? Hopefully more people can attend that, honestly. So let's see here. So we said our horizontal stabilizer would be 5 inches. As I said, we need to do half of that, 2.5. That's what we want to do, right? And as you can see, there's a 5 foot span right here. And cord, we did, let me check, 5 inch cord. So elevator, we don't need it to be, the same cord as the wing. That would just make it oversized. So this is like around 3 inches. Honestly, sounds pretty good. We'll just take the 3 inches. We also need to fix the top at 3 inches. I'll just set the offset to 0. We're just doing normal stuff for now. And typically, you want like a flatter airfoil for it. As you can see, 2414 was a little bit curved, and then E216 was really curved. So what you don't want your empennage to look like is something like this. I'll just find the top and the bottom. So from what I know, you never want empennage, at least for our purposes, to have a lot of, I'm pretty sure it's camber. You don't want it to have a lot of camber. You want it to be pretty flat. So something like this. Hopefully it'll change. Taking a sweet time. Yep, flat like that, right? Save. Also, another thing, we want the distances for both of these, the elevator and the fin, to be the same, right? We are doing a pretty small plane. Typically, these values are given to the aerodynamics team from structures, right? So we're, we're modeling a pretty small plane here. So we don't need it to be like 25 inches. You could maybe do it like 18. 18 would be. Both of these need to be the same. Fin, choose again. We typically do the same airfoil for the horizontal and the vertical. We can look into doing different ones. So before I decide, it's fine. So what if we decide would be 4? So okay. So yeah, there are some inaccuracies with XFLR when it comes to this one, because as you can see, for the other ones, it goes on both sides of the axis, right? On both sides of the x-axis. For the vertical, you only need one. So sure, you enter say 2 here, and it gives you 4 here, the span, right? But this is usually inaccurate. What you enter here is going to be the actual value, to my knowledge. So I will enter 2, you will see 4, right? But it's actually like, okay, yeah. So if I want it to be 4, I want it to be 4, I'll have to enter 4 here. Hopefully, yeah. So this is 4 inches, right? It says 8 inches. That's it thinking that it's on both sides. It's overlapping on both of the axes. Just on one. This is 4. We said what we want 009. It's just a matter of finding that. 009. You have to set the top and the bottom. So we'll zero out one offset. And forward, we'll just do the same as usually it is the same anyways as the vertical as the horizontal stabilizer just speeds things up, honestly. Ooh. So yeah, sometimes we eyeball these dimensions, we do research into these dimensions, and then turns out, oh, look, one of these might be too big. So then we go back and we just do it again. So we decided four, let's try two, right? Okay. So let me correct myself. I'm honestly, a lot of this is aerodynamics is a very vast topic, and sometimes I do this. So I said two, gave four. It's completely accurate. Disregard all the inaccuracies I've had before. So yeah, that looks better, right? And now we have a plane that we can analyze. Okay, right? And then also click this. It's going to delete. Well, oh, it's not. This is out. This small little plane here. Um, so now I will get into some of the more advanced analyses. But before that, point masses. You actually need to set masses for like each part of the plane. So this right here would describe like the motor, the payload, and then the avion. Well, yeah, this is like the payload and the avionics. These two. I'd assume this is the avionics because it's the mass is more, obviously. This is the payload. So yeah, we need to define them. How do we define those? We go here, click on our plane, edit, plane inertia. So additional point masses, that's where we add. We have a pretty small plane, so that means we're not going to use a terribly strong motor. Let's see here. So we can say 0.5. And then inches, this is like more of like the location. Let's roughly base it off of this. So let's say like 3 inches and like -6 inches or something. Really just going off the top of our heads. It's more um, getting to the analyses is more of the important part of this workshop. So mass here, this is the payload 0.48. I'll do like half of that, 1.25. And then let's see here. I'll say like -5 and like 2. 5 and what else? Right. And then we also have to add mass to the wing. So we have a pretty small wing. I'll just say like it is in kilograms, so it's pretty, yeah. So let's say two. Elevator. You know, and I'm kind of really just pulling these numbers out of the top of my head, but typically these numbers are given to us by through just like testing and see what materials we want to use, and also like working with structures, right? For the fin, let's say, and you have to define those point masses if you want to do any of the more advanced um, analyses, right? And then LLT, that is the first analysis, advanced analysis. How do you do that? Well, before anything, you click save, right? You just added a master plan, means you need to save it. Analysis, define analysis, so LLT analysis. You want to say it's type 1 fixed speed, say this particular case, not going to go terribly fast, 100 miles per hour. Analysis, you want to set to wing only, inertia, all these other stuff stay the same. Density of air, that's like a given. That's like a constant, honestly. So yeah, and you can add some altitude and temperature, all that stuff. We could do this honestly, more around the time of competition. So yeah, and then it gives you this, and you need to click. Make sure this is selected. This it goes from -20 to 45 at an increment of 0.1. For anything, I will save. Give it like a minute so that it doesn't crash. You can different ways to move around the plane. So what I did was I clicked Control and then left click. I can move around here. And you can just click and drag. You just want to get it from a different part angle. Want to rotate it. Then Control and then click. So it's safe. LLT, we'll look at more details about what an LLT is after this analysis is complete. So it goes through every angle of attack, right? LLT is supposed to give us the stalling. That is the main reason why we do an LLT. And I'll keep going until it experiences an error. An error. Hopefully you're not finding this too boring. At 35 now. Go. And then it should give us the stalling. And click close now. And yes, we just keep scrolling down until we find our strong stall angle, which would be the last number you see. So this plane, which is kind of crazy, honestly, is a stall angle of 32 degrees. That means as it's ascending, it will only stall when it's 32 degrees in the air. That's if it initially starts at -6. So that this is like I think you can use this as like sort of this initial number as like a margin of error. So it's like plus or minus 1.6 32, right? Or 32, right? Because honestly, in real life, it's not going to be as exact as analysis, obviously. So it's good to have a margin of error. And so the main stuff you can get from an LT analysis is coefficient of lift, accurate coefficient of lift with the entire wing, only considering the wing, not the horizontal stabilizer or the vertical stabilizer, only the wing, the coefficient of lift, and the angle of attack. The the coefficient of drag to the coefficient of lift. Um, Previously, what we saw was all this data for the airfoil itself. This is for the wing, right? So, so um, next would be to um, what do we do next? That's open pop up. All right, I'll be back in a moment. Andy. All right, guys, I'm back. Sorry about that. Just had something pop up. So back to this and then LLT, right? So as I said before, previously we got all this information for the airport. What we're now doing is getting the same information, but for the entire wing. Right? So how do we view this information? We go to these graphs right here. So this is C. Okay, right. So we want to look at only our workshop plan. So look at all of these. And right here, we have some nice little graphs of coefficient of, okay, we're seeing coefficient of lift to coefficient of drag, really stable, right? Not going anything crazy. As one increases, the other increases, fair enough. Coefficient of lift to alpha, also stable, increasing. Um, all right. Sorry guys, I keep leaving. Just got like a little ruckus going on because I have an exam tomorrow on a Saturday. It's raining a lot, so that all that needs to be arranged. And um CM to alpha. Okay. You can look into what CM is. I'm learning with you guys. Is aerodynamic. I'll probably understand it. Oh wait, yeah, it's the pitching moment. Yep, just forgot. Okay, so the pitching moment to angle of attack, right? So if you start at zero, the pitching moment will be zero, right? but as the angle of attack increases, it just goes up and up and up, pitching moment. Right? It's just a numerical value to explain how much you're tilted up. And then coefficient of lift, the ratio of lift to drag to alpha, which is the angle of attack. It's pretty stable. It sort of gently decreases as the angle of attack increases, right? Is typical, right? Stability decreases as you try to ascend, as you experience more turbulence, all that experience more turbulence. You're at a steeper angle, so you need to push more, you need more thrust. Um, yeah, it's as expected, honestly. And it's you can read this one. It's a type 1 polar. So looking into what polar actually means, 5 miles per hour, and it's an LLT analysis. That means it's only considering the weight. And next type of analysis is the VLM1. Right? This takes into account tail interactions. It prepares us for a proper stability analysis. And then it gives us our first 3D flow model, which helps us visualize just normal drag, induced drag, pitching, yawing, and rolling moments. And then it also gives us some aerodynamic sectors. This I'll look into how to actually get that from XFLR5, and what it actually sort of means. Francesco may know, our chief engineer, maybe not. Emir may know, our product manager. We'll see. But for now, we're really just focusing on these two things. So how do you do a VLM analysis? You go to analysis, define analysis, and I'm pretty sure I'd say, yeah, fixed speed, force field vortex, VLM1, um, no side slip, inertia, all of this should remain the same, right? Hopefully it will work. Oh, wait, okay. I did on the wrong click. So I was selected on the plan for E392 when it should have been our workshop plane. So I'll just go back. Analysis, define analysis. Again, force field vortex, BLM1, side slip, all that has. I'm pretty sure all this can remain the same. Save, and then analyze. Pretty fast. And then let's see what this helps us determine. As I said, pitching, yawing, and then it helps us visualize, induce. Okay, yes. So I will try to find. I can say induce drag. Hopefully it works. I need to save. Experiencing lag. Display. Okay, so okay, so it does give us these CL and CD values, as you can see. Um, Sometimes it does stuff. I'm not sure why it's not showing us any extract, but I'll try to. Yeah. Okay, yeah, maybe, yeah. So the induced angle, right? It's due to combination of factors due to drag, the Reynolds number, all the other forces all the other things that are going on with the plane, right? And it's like, oh, the wings like sort of like, nah, okay, going up and down. This is how much you can expect it to like tilt side to side, right? Roll, I guess you could say. It's like slipping at negative induced angle, going side to side. It's hard to explain now. We'll look into it later. Said as like workshop. Um, yeah, a lot of this will be maybe I'll go back. No, that's- let's say like this to reduced. Okay. Okay. All that's things. What is going on, guys? Um, that's fine. Okay. Oh, okay. Yeah. I think I have to click reset this. All right. My best to this makes sense. Yeah. Okay. So you can animate it through each angle of attack, and then you can see the CL and CD increase. I'm trying to get this induced drag to work. I don't know. Maybe we'll get that. Be able to see that in a future workshop. However, we did get a 3D flow model, as you can see. That's why all of this is working. Just that I can't really figure out how to get the raw data for this and this. It's fine. We have time. We'll figure it out in the future. So the second analysis is a VLM2, right? And I'll try to end around like 1:30-ish. Then we'll cover more in a later meeting, honestly. Um, yeah, okay. the final analysis. Before we do a VLM2, some things to clarify. Um, so a VLM2 is the best way you could put it is like a more accurate version of VLM1 because VLM1 has something called um, flat wake. And what is wake? Wake is like the vortices at the tip, right? So um, when you're flying, right, due to induced drags, I mean, parasitic drag, which is like the drag you typically do not want. There's these vortices that form at the tips of the wing, and then it's sort of they're bad for the lift and like being able to fly and all that. So that plus the downwash, which is like the downward movement of the airflow behind the wing due to the lift, right? So um, as the force, the pressure of lift makes the wing go up, the air behind the wing is going to move down, right? And that's obviously going to affect the how the wing is able to make the plane fly. So I'm trying to um, make it well. Yeah. So let's say looking at this one, right? So this sort of explains what downwash is, right? As we said, the um, the airflow, right? The downward airflow behind the wing due to the lift, right? So the lift right here is causing the airfoil to move upward, right? But behind the wing, there's air moving down. That is what I'm trying to explain, right? Due to it going up, which is because of the lift. And then the VLM2 also gives us a more accurate pitch moment at different angles of attack. What that means is that go to these graphs, right? Graphs, um, all graph settings, reset, reset. Okay. Say I want like graphs. Yeah, or- yes. So pitch moment, right? It would give us a more accurate pitch moment. Right? So what that means is that this pitch moment graph would just be more accurate. That's like the main thing of what I'm trying to say, right? So this is useful for like non-simple geometry in cases where flat wake is bad, right? So what is flat wake, right? That is basically saying, oh, all this air is just like moving perpendicular, like not perpendicular, but like in parallel to the airfoil, which is not how it is, right? It can move up, it can move down, it can be perpendicular, it can go anywhere in relevance to the airfoil. It doesn't need to be parallel. Right? And the more tainted geometry of like a wing empennage, the more inaccuracy you'll see in your data if you assume flat wing, right? So, and yeah, as I've said before, it does everything a VLM1 would do, but more accurate. So, um, uh, it's been kind of iffy trying to read the graphs so far. So I'll just like move forward with how to do the analysis itself in XFLR. Just fairly simple. And we're also short on time. Maybe in a future workshop, we'll look more into how to actually read these graphs. I also have to fix my graphs because I messed something up. But yeah, how to do VLM2, a ring vortex. We'll also look into like what these names actually mean. We'll keep everything else the same, I'm pretty sure. Ring vortex, VLM2, click save. Okay. What? Still, yeah. Okay, from the same amount. Let's see the difference here, actually. So slightly more, I guess. CL negative C. There's any difference? Well, we have to start here because it did give an extra. It did give an extra angle. It says 0.412, and here 0.553. So this is assuming that the air is just being perfect, right? It's just completely parallel to however the wing is. So the wing right here is at an angle of attack of negative 12.5. This is saying that most of the air is also at an angle of negative 12.5. It's like perfect conditions, right? Which is not always the case. And this is saying BLM2 is that, oh, the air is doing what it wants, right? Therefore, your coefficient of lift might be lower. Same with your coefficient of drag might be lower or higher, right? You look at this one. Coefficient of drag 0.232. Coefficient of drag 0.271. See, there's an increase. Why? Because weight change is taken into account. And as we did, this is what wake is. Um, Stability analysis. I will try. We have like 10 minutes left. I'm probably going to end it at like 125, honestly, because this is like going on for a long while. We all got stuff to do. This will be carried on in the future, these stuff mostly, and also a better me just explaining the graphs better. I might get help from other people to do that as well. Um, yeah, but this is basically a rundown and most of the analyses we do in XFLR and how we use it. And it really shows why the software is useful for what we do. So, yeah. And now for my desperate attempt to explain what a stability analysis is without actually doing one because it takes forever. So, a stability analysis is basically multiple VLM analysis done, and then the derivatives of that data. So, you know how it graphs a line and stuff, takes the derivative of that data, and it gives us the changes in lift and the drag. What does this give us? Trim data, stability derivatives, which is like basically response to turbulence, fluidity. We can actually, I'll probably remember fluidity. What is this? Fluidity, aerodynamic. I misspelled aerodynamic. Vehicle's aerodynamic surface being overall, it's the sensitivity. It's the sensitivity. Oh, wait. It's the sensitivity of um our airfoil, our wing, our horizontal stabilizer, all that. It's how sensitive it is to changes in the environment, right? And then control derivatives, which is like how strong the control surfaces are. Um, it usually requires a separate stability analysis because this doesn't really reflect, right? the shape of this wing doesn't really reflect a control surface. If you had a control surface like an aileron or something, or aileron flaps, this ending here, the ending portion here would be like at an angle. It wouldn't be like completely fat. It would be like sort of like this, right? And that would help us have more control when we're trying to pitch up, pitch down, roll, all that jazz. And then honestly, a dedicated CFD software is better for this than an XFLR analysis. But we do one anyways because it's easier to get this done than this done because we're still working to figure out how to actually do these CFD softwares and actually use these CFD softwares because it is our first year. And frankly, that would automatically elevate us above a lot of the teams if we manage to pull that off. Because a lot of them just stick with XFL5. And then see, it's like in the past, the stability analysis used to be really inaccurate, but they've made some improvements, right? This is just based off of like research, and what I've seen on the website. Airfoils retain geometry when saved and reopened. Basically, what used to happen was you would make an airfoil, you'd save it, and then you'd reopen the file, and then it would be like all over the place. And then there's no more mass errors when running a stability analysis, and there's no crashing when running a T7 polar, which is like the polar that stability analysis use. As I said, we're looking into what these polars actually mean. I've been doing this for 2 years. There's still a lot I need to learn. There's a lot that y'all can learn, honestly. Um, yeah, yeah. This is like the first workshop. Hope it's not too boring. And yeah, honestly, see y'all later. Just told to tell y'all to like and subscribe. Please do that if y'all can. I'm gonna stop sharing my screen. Uh, yeah, yeah. See y'all later. Sign off.